Now recording. So, how is everybody today? Awesome. Good Friday. Good grief. Hopefully assignment 3 isn't giving you too much grief. How is assignment 3 going? Have you guys started on it yet? Yeah? How's it going?
Solid. I haven't heard too much yet on it, but
Done, though I have a couple questions.
Okay. Are they like specific to your implementation, or are they like interpretation of the document type questions?
A little of both, I guess.
Okay. All right. Well, I can take questions on assignment 3. What are your questions?
Okay, so the validation, I had it attached to the actual input box rather than as part of the like, submit button kind of thing.
So you implemented validation in HTML rather than JavaScript?
No, it is JavaScript.
Okay.
So like if there's an on-change component that activates the JavaScript for like, I used a number type of input
Sure.
field.
Yeah.
And so if there's any value that isn't like either too low or too high, it will automatically reset to like either the minimum or the maximum. And then later on the submit button is another function that doesn't take that.
This is okay. So this sounds good. If you want to go one further step in terms of validation, there's one more thing you can do there. Leave your source code alone. In the inspector, when you have it loaded in the browser, change the input type to text and see how it handles a string input. Because you should always view your input types as suggestions. It's not like the horrible sad truth is, even if you use something like a slide bar with like a min and a max range, the website can still be, like someone can hack the website in order to put something that's not a number in there fairly easily. So if we're thinking about validating inputs, that's another angle that we should be considering. Does that make sense? Any other questions?
I'll have to go back and look at it.
Sounds good. Does anybody else have any other questions about assignment 3? Okay. So, our material today, we are going to be jumping into Module 3. Module 3 is, well, the objective of Module 3 is to teach you how to work with the DOM in a more object-oriented fashion. Particularly, we will be, like the big main takeaway from Module 3 is the creation and destruction of sub-objects within the DOM using JavaScript. We will be covering this through the medium of scaled vector graphics. So we're kind of at this point in the course where this course is having a slight intersection with Java, and then we'll continue off and differentiate the course later. Scaled vector graphics is the same engine which underlies JavaFX, which I'm sure all of you have considered to be a royal pain in the keister. I will show you SVG. I think you'll find it's a bit easier to get done what you want to get done in just straight SVG rather than in JavaFX. But basically all of this comes with the great big disclaimer. No person whose profession is graphics design would ever design an SVG file using text editing, right? It's simply not done. Like, you use a GUI, you use an image editing tool to edit images. You don't, like, go in and modify the plain text of a document to produce an image. It's just ludicrous. It's a ludicrous way of doing things. However, within the context of this class, the reason that we're going to be doing SVG graphics is that you can use the same mechanisms or similar mechanisms to grab references to SVG objects the same way that you do HTML elements. By doing that, you can perform similar manipulations. You can attach them to event listener, or reverse that, you can attach event listeners to SVG objects. You can pull their attributes in with JavaScript. You can set their attributes using JavaScript, and you can create new ones using JavaScript. This is all, the purpose of all of this is to build you towards assignment 4. Assignment 4 asks you to create a small video game. Emphasis on small. Like, if you guys even reach the level of an Atari game, I will be impressed. Right? Like, Space Invaders would be quite the accomplishment. All right? So, yeah. Any questions about that? So far, so good? Everybody's looking at their screens instead of me? Okay. Hard for me to read the room if nobody is actually paying attention forward. So, are you all working on assignment 3? Yeah. Well, while I don't condone it, I understand it. I would ask, though, that you, pay some attention. Just, divide your attention between your homework and me, please. So, in order to work with vector graphics, we should understand what vector graphics are. So, going back into the history of computer graphics, there have always been two main competitors. Perhaps you've heard these terms before, perhaps not. Raster and vector. How many people have heard of the term raster before? Yeah. So, to explain the difference between raster and vector graphics, well, I can summarize it shortly. Rasters are large two-dimensional arrays of pixel values. Vectors represent graphics using mathematical equations. That's the main difference. But to illustrate this difference, we should consider the development of display technology in computing. So, does anybody know how a modern monitor works? A modern flat-screen monitor, such as the ones you find before yourselves. Anybody know how they work? Not one person?
Lens.
Hmm?
Lens.
Yes. So, essentially, if you can actually, on a monitor of sufficiently low resolution, you can still see this if you look really closely. But if you have a modern monitor, you will have a very large array of LEDs, light-emitting diodes, tiny little cells containing light-emitting diodes. If you were to expand, magnify many times, you would find that you actually have a cluster of 4 of them. You would have R, B, G, and W. So an LED providing the red, blue, and green components of the color that is being meant to be displayed, plus some monitors do this, some don't. You often have a white LED there, which essentially provides brightness. It doesn't modify color, but when you turn the monitor's brightness up and down, that's typically, that's one of the ways they do it. Doing it this way, you get like a nice rectangular grid. Otherwise, you know, there are some monitors that sort of will do things in a sort of a triangular tessellation, so that your pixels sort of form in a triangle grid like that. That's if you exclude the white LED. But at any rate, this cell in the monitor is fed red, blue, green channel values, typically when we represent things in hexadecimal. You know, if we have a hexadecimal color code, we have 2 characters for red, 2 for blue, 2 for green, right? Because it's hexadecimal, right, each one of those characters represents 15 bits, right? So, or 16 bits from 0 to 15. So you get, in total, right, 2 to the 8 different color representations using typical RGB. So it's like 1 byte. You know, 2 hex characters is 1 byte. When you do a hex code, like you're choosing a custom color in CSS or something like that, that's a byte for red, a byte for blue, and a byte for green. Those get fed to LED intensities. That's how the monitor works. Does that make sense? So this is the digital version. This is how raster graphics work, right? You're dealing fundamentally with a great big array of pixel values. In fact, you're dealing with 3 individual arrays of pixel values, a red channel, a blue channel, and a green channel. This is different. So vector graphics work very differently. To understand vector graphics, we have to, well, one way to understand it is to examine a slightly older, but at the time very popular, technology for displaying images. Does anybody know what CRT stands for?
Cathode ray tube?
Cathode ray tube. Yes, absolutely. So, you know in like old movies, you see these screens that are like rounded, right? And like you often see like scan lines going down them, right? Those are cathode ray tubes. So the way that a cathode ray tube works, at the back of the monitor, you have an electron gun. This electron gun fires electrons. It's like a little laser, right? Almost like a little laser pointer. Now, electrons, of course, are electrically charged, right? They have, does anybody know, are electrons positively or negatively charged?
Negative.
Negatively charged. What are positively charged? Protons. That's good. So, the electrons are passed through a series of electrically charged plates, one in the horizontal direction and another in the vertical direction. By passing through these electrically charged plates, the electrical charge on the plate is controlled, by the way, the electron beam can become deflected and strikes the surface of the monitor. the monitor is covered in photocells which absorb electrons and emit photons, right? So the electron goes in, and a photon comes out, and that's how the monitor works. So when you have a cathode ray tube, if you're displaying something like television images, right? This electron beam is scanning the entire screen, very precisely hitting photocells which emit different colors of photons, right? You'd have R, G, and B photocells on the screen, right? Unless your set is old enough that it only has monochrome, right? If you're displaying something like a television image, you're scanning that entire surface, you know, however many times a second, 30 times a second, 60 times per second, right? But that's not necessarily the only mode that you can do with a cathode ray tube. It is possible to take that beam of electrons and simply carve a line across the screen, right? Not do a scan lines, but say, start here, move there, right? Doing this, you can trace out lines on the screen, and so long as you retrace those lines sufficiently quickly, it gives the appearance of lines being permanently on the screen. So if you think back again to old movies, you know the radar, that they have on like old ships, and it's like, it does this scan thing, and you have like blips in it. Doop, doop. This is the type of thing that you can do with a cathode ray tube that you can't really do with one of these, right? At least not natively. You'd have to emulate that ability, right? So that's why, like, for a very long time, cathode ray tubes, like, were used for display technology. You can hook them up directly to analog signals and display them, right? So this kind of comes back to one of the oldest fights in electronics: analog or digital, right? Over time, digital electronics have won. I think we can declare their victory at this point. Basically because they were miniaturizable, right? Analog electronics were not miniaturizable to the same extent, although again, great strides have been made, as the technology has continued as well. But basically, when we're talking about vector graphics, we're talking about an older form of displaying things on the screen. Something that dates back to the analog methods of displaying images. All right? So that's all fine. Would you like to see some example? An example? So, of course you do. I'm about to show you a picture of a video game. So, there's one old Atari game which, as opposed to all those new Atari games, there's an old Atari game which very nicely exemplifies vector graphics. Can I turn that off? Good grief. There we So there is an, let's see, pardon me for a moment. Thank you. So, would somebody at the back mind killing the lights? Thank you. Thank you, kind sir.
Where is it?
Oh, it's just yeah, hit the biggest button. Right. So this is a game called Tempest. This is the arcade version. Oh man. Still too much light in here. Do you mind? Yeah, thank you. That's the wrong one. There we go. That's better. So this is Tempest. A little bit better. So this is the arcade version. I will demonstrate the difference between the arcade, the difference between raster and vector graphics by demonstrating the different, the arcade version versus the home console version. So it seems like, if you look at this, it's pretty obvious that this is vector graphics, because if you notice, like, where lines intersect, they're actually darker, as if the electron beam has gone over it twice, right? So essentially, one of the advantages of vector graphics over raster graphics at this point in history is that vector graphics can be scaled. You can scale it because all you're doing is applying a mathematical transformation to mathematical formulas to get that difference. You can see how the little bow tie looking enemies, you know, are coming closer. You can see how the level is like zoomed in and zoomed out as you travel through space, right? Let me tell you, in the 70s, this thing was this was the GOAT video game, right? For the time, these types of effects just were like, they would destroy your brain. And for a period of time, it was thought that vector graphics they would eventually win, just because you could do so much better visual effects with them than you could do with raster. During this period, they were also experimenting with three-dimensional simulations, like little like turret games where you had to blast enemy spaceships that would fly in a 3D fashion. A little bit like Star Fox, actually. These are the types of like games they were experimenting with using this technology, right? But like, you know, you can see this looks pretty good. Even by modern standards, that's not a bad looking video game, right? You guys want to see the home console version?
Of course.
Atari, oh boy, Atari 2600. Oh, oh, bloody ads. Man, I hope that this doesn't affect the video. Maybe I should, because I'm recording this. There you go. All right. Maybe I'll put the ads, but. Big. There we go. So, we've suffered a slight degradation in quality. Yikes is right. I'd also like, it's almost impossible to even tell what's going on in this. You know? Like, there was a reason people went to arcades. You know? This was completely unacceptable. By the way, you know that lovely like zoom through space animation when you finish a level? That's what the equivalent was in the home console version. Is it flashes this thing yellow, and there's only one level in this. That is the level. This is the only level. And like, I'm pretty sure it doesn't even have all the enemies. Like, you know, you had like those lines that were coming down, you don't get that either. So like, you know, when you hear people talk about the home console version, this problem was basically a problem until like, roughly, like N60, not N60, like Super Nintendo kind of territory. Although the TurboGrafx was like quite an expensive and nice machine, and like probably during the Nintendo Sega years probably came closest to the arcade experience. But you can see that basically what you're dealing with here are pixels, right? And quite a low resolution of pixels as well. So like at the time, if your options were the vector graphics version of Tempest in the arcade or the raster graphics version here, you can see why in the 70s they thought vector graphics were going to be like, they were going to be the thing to take the cake, you know? But then, processors got smaller and faster. Memory got cheaper. And within a few years, you have, oh man, I'm gonna turn off the screen until after the ad is loaded. Oh, it didn't even do one. Okay. There we go. So this is a game called, there we go. This is a game called Space Harrier. Space Harrier is notable because, anybody who knows their video game history is immediately thinking Mode 7, right? So this was kind of the turning point for raster graphics. You can see that essentially what we have is a bunch of sprites, right? We have a bunch of raster images. What was developed to make Space Harrier possible was a co-processing chip which accelerated scaling of raster images. Now, it only downscaled. So every image that you see, like in memory, it's the full-sized version, and then they scale it down to simulate depth. That's how Space Harrier works. But like this really like strongly destroyed. Like you can see the dragon. This really like when this came along, vector graphics were basically done. Right? Because this looks so much better than Tempest, right? But yeah, so that's you know, and at the same time, it's like how many different ways can you do Space Invaders, you know? But so yeah, this type of graphics scaling. I don't know if it was the same chip that went into the Super Nintendo, but the Super Nintendo, one of the huge advantages of it over the NES was that it had quote-unquote Mode 7, which activated a similar coprocessor that allowed the scaling of images. But the Nintendo chip didn't just allow you to like zoom in and out, it also allowed you to do like transformations front back, it allowed you to like flip things around like that. If you want a good example of mode 7, actually just the opening. Oh, more ads. Bloody heck. Ugh, go away. I'm gonna put you over here so that I can see when the button appears. Come on! Oh. My hatred. My hatred! There we go. Alright, so I want you to, there's an effect that they play at the beginning of, at the opening of Legend of Zelda: Link to the Past, which demonstrates what Mode 7 was capable of. And it has to do with the spinning triangles. See these spinning triangles? That was absolutely not possible on the NES. That would have been a lot of work, right? I'll show you that again. That's spinning, that's Mode 7, right there. So, and it's interesting because you've got like very early 3D games that used Mode 7 to do like proper 3D, such as Star Fox. But yeah, so does everybody understand the difference between vector and raster graphics? Yes? Good? Good. So, so you may be saying to yourself, okay, sure. So vector graphics, we can, somebody at the back, could you give me a little bit more light? Put it at light level 3, if you don't mind. Thank you. So, assignment 3, rubric. No. Get out of my face. There we go. So, you may be asking yourself, okay, so raster 1, so why are vector graphics still relevant in the year 2025, so many years after the deployment of Space Harrier? And the answer to that is scalability. Well, there are two. So, although raster eventually won, generally won, there are two problems with it that vector graphics do not share. So, two disadvantages of raster graphics, right? Number one, the files are friggin' huge, right? You are representing a huge array of pixel values, right? 3 of them, in fact. Does anybody know how many pixels there are in a modern monitor? Anybody, let's just take standard HD, right? HD, 1080p, pixel dimensions. So it's about 2000 by 1000, right? Maybe if I put that in there. There you go. So, the number of pixels it takes to render one screen in standard HD definition, which, by the way, is getting kind of small at this point. You need 2 million individual pixels. Each pixel is represented by an array of, well, either 8 bits or 16 bits. Let's say 8 bits, right? or 1 byte for each of the 3 channels. So multiply that number by 3, right? 6 megabytes, approximately speaking. That's how big a file size has to be to encode, to represent everything on a screen. Now, file formats do quite a lot of compression, right? Like, there are really only a couple of file formats where the pixels are being stored in raw pixel values. Does anybody know what they are? Any guesses? Well, you've got one format that's actually called RAW, but there's another one called bitmap, which is an older. If you're old enough and you used to mess around on Windows 95 machines, you may have seen the term bitmap floating around. JPEGs are a compression algorithm. PNGs are a compression algorithm. All of this is trying to take those 6 megabytes representing the full screen image and shrink those down as far as possible. But at a certain point, you hit an information density limit. You can only compress so far without losing image data, and that's what that's what the problem with a poorly compressed JPEG is, right? That's why it has all those weird artifact pixels around the thing, is because fundamentally you require so much data to represent something, right? You can't, if you start dropping information, But anyway, so vector graphics, the size of the file, the size of the data that you need, is proportional not to the size of the screen, but the complexity of the image, right? The more, if you draw a simple circle, right? If all you're doing is a circle, with a bitmap to occupy this screen, you're talking 6 megabytes. If you're talking about a vector, like an SVG graphic, 40 characters. Right? Maybe. If you do some other stuff with it too. So much smaller. So it takes less network time, takes less bandwidth to send smaller things. So in an internet context, in terms of speed and having to pay for server time, vector graphics are generally preferred. Right? They're faster and more efficient. At least for images which are below a certain threshold of complexity. Now, if you have a complicated image such as a photograph, you can produce a vectorized version of that raster graphic, but it will occupy more space, quite a bit more space, than just a regular bitmap, even uncompressed, right? Because at its limit, rasterization would be producing a small square for each pixel, giving it a color, right? It's a less, it's much less compressed than just individual pixel values, right? So another advantage of vector graphics is that they can be scaled infinitely to any resolution screen with no loss of fidelity. With a bitmap, you only, if you zoom it to any degree beyond its maximum size, which is 1 pixel value per pixel on your monitor, it's going to start looking more and more like a Nintendo Entertainment System game, right? It'll just show you're just blowing pixels up, and the pixels get bigger and bigger and bigger as you expand the image. It looks like crap, right? It doesn't look very swish. Consider logos. Let's pick this assortment of logos. Which, as we can see, is this raster or is this vector? Is this raster or is this vector? Serious question. That's raster, yes, very good, thank you. So, which kind of shows that the people who put together this website didn't know what they were doing, but that's okay. So, if you consider these logos, right, corporate logos, or just logos for things in general, you'll notice a few common features. Number one, they tend to use a small number of colors, right? Most of these use at most 3, maybe 4, right? Microsoft uses 4. For the ones that don't use, just a couple of blank colors, they're using gradients. And gradients can be set up with mathematical formulae. They are also something you can do easily with vector graphics. So, for example, the little shine on the Facebook logo, that's a gradient, right? That's a couple of gradients. There aren't even that many on this. This is a gradient. You can color transition through colors using gradients. The shine on the Volkswagen, that's a gradient. This is a gradient, that's a gradient, right? Another thing, the shapes tend to be simple, right? They are most simple if you're looking at things like this. A bit more complicated geometries, right? This one's quite simple. These get to be, things that are sort of more representative tend to get a little bit more complicated. But in general, writing a mathematical equation to describe the outline of the object, not that difficult. Not that difficult for most of these. Most of these are just circles and squares, slightly rearranged, right? This one is just 2 splines. And we're going to be talking about splines later on as well. But, yeah, this one's pretty complicated. I wouldn't want to have to do that one. So, when it comes to logos, if you do a vector graphics version, it can be scaled up and down infinitely with no loss of fidelity, and the image size itself will be quite small. Does that make sense? So, there you go. I also wouldn't want to do the Starbucks logo. That's a bit more complicated as well. So, if everybody could please open up their favorite code editor or open a new tab in the one that you're currently using to do assignment 3. Let's make ourselves a new HTML page. Let's call this svg example.html. There we go. let's throw a little bit of HTML in here. Can you see this at the back? Thank you. So, the way that we create an SVG graphic embedded within the HTML document is as follows. Now, do I need to slow down? Am I going too fast? So you create a new page element, SVG. Now, one thing that I should note before we get into this, it is my suspicion that the rendering engine for SVG graphics is a separate sub-process to the one that's rendering the HTML. You will find things that you get away with in HTML you won't get away with in SVG. It's a lot more persnickety about syntax. We're going to see this as we go through, but one thing in particular, most of the tags that we'll be using are self-closing tags. Things like a circle or a rectangle, those are self-closing tags in SVG. If you don't put the final slash in for a self-closing tag, the whole thing just blows up. And like normally you get away with it in HTML, you know, not putting the self-closing tag in, not putting the slash in for a self-closing tag, but here you are not so lucky. It's a lot more strict on syntax. So, the way that you, or one way at least, that you can control how, like, the dimensions of the SVG image is using CSS. You can think of this, the analog in JavaFX. You know how, like, you declare the window size outside of the graphics context? This is like analogous to that. So we can make an, oh, I need a style tag. What am I even doing? Style. Here we go. SVG. Order. 1 pixel solid black. Width. Oh, let's do 800 pixels. Height, let's do 600 pixels. And just to make it look nice, I'm going to make display mode block and margin auto. There we go. So now, if we render the page, that's actually still a little bit too tall, isn't it? Let's make it 500. There we go. Behold, an SVG graphic. Currently doesn't contain anything, but there you have it. So, let's draw some basic shapes. Some basic shapes registered trademark. So, I hope that you guys will find this to be slightly preferable to JavaFX. To draw a rectangle, you create a new self-closing tag, rect, x, y, 50. X position, y position. Width, 50. Height, 100. There you have it. There is our square. Rectangle, pardon me. Good. Now, secondly, perhaps we want to control the color of the thing. Well, we simply declare a few more attributes. Phil, somebody give me a CSS color. Everybody always says orange.
It's too basic.
I mean, I don't know. I'm expecting people to like pick out the weirdly named ones because that's fun. But like, you know, it is true that the set of CSS colors is a proper superset of the set of like normal colors. But all right, stroke. At the back, sir, you had a CSS color.
I was just gonna say like teal or whatever.
Teal. All right. There you go. Stroke and fill properties create color on our new objects. So you'll see that this is, you know, slightly more compact notation than we have been doing so far in JavaFX. Very good. Let's now do circle. Circle. So circle is a little bit different. It requires CX for the X position of the center. So it's 150. CY 50. Width, sorry, it doesn't do width and height, it does R for radius. 35. Fill, someone give me a CSS color.
Purple.
Purple. Yeah. And that would be enough. And there you have it. A purple circle. So, so far so good. We also have ovals. There are a few more properties listed in the notes that I'm going to be going through in class, so you know, I'm kind of hitting the major ones. For complete reference, please, you know, well, actually, for complete reference, go look up the documentation online. But for a slightly more complete reference, please take a look at the notes. Like you can do things like round the corners of the rectangles and stuff. Let's take a look at ovals. So the way that you do an oval, ellipse. Now, ellipses kind of make me angry. All right, the way that they do ellipses here kind of makes me angry because it's not correct math, but I'm going to show you anyway. CX, let's make that 150. CY, let's make that 200. They do an X radius, or I think it's radius X, and a radius Y. Right? Uh-oh, it's not working. Anybody see where my syntax error is?
Forgot the dash in
Yes, I did. So let's put the slashes in. Slash, slash. Oh no, it's still not working. And the color went away. You have to include the spaces too. There you go. Oh, I didn't give this a fill. Someone give me a CSS color.
Cool.
Yes sir.
Dark salmon.
Dark salmon. Wow. That's good. So I'm doing a thing here. You may have noticed me doing this before. It's somewhat important to know when quotes are necessary and when they're not, right? You'll notice that I haven't used a single quotation mark so far in any of this. You are not required to put the double quotes in unless the thing contains space characters, right? So in XML, this is both HTML and SVG are written in XML, by the way. The space character is your separator between attributes, names of elements, all of that jazz. If the thing that you're assigning to the attribute itself contains a space, then you need to put it in quotes. Otherwise, you can leave the quotes out. Now, because I'm a little bit superstitious, I will include the quotes anytime I see any kind of separator whatsoever. So if the string includes commas, semicolons, or colons, I will also put things in quotes, just in case something might go wrong, right? It shouldn't, but you never know, right? So there you go. I just saved you collectively, probably, between everybody in the class, I probably just saved you like a year or two of typing quotation marks over the course of all of your careers. So there you go. So let me explain why ellipses are done incorrectly in SVG. Does anybody know what the mathematical definition of an ellipse is? Shall we start with the mathematical definition of a circle? So what is a circle? Someone? Who? What? Yeah? Did you say? Who? Yes?
All the points that have the same distance from one point.
Yes. All of the points that have the same distance from a central point. So that is the radius, this is the center. The circle itself is all of the points that are of distance r from the center. With an ellipse, an ellipse is a circle with two centers. Right? So an ellipse is defined as all of the points which are, if you take the distance to the two centers and sum them, the ellipse is the figure where all the points have the same combined radius to the 2 points. That's what an ellipse is, right? So any point on an ellipse, if I take A and B and I sum them, I get the same number. That's how mathematically an ellipse is defined. And ellipses also have another very interesting property, which is if you take an ellipse and you take the 2 center points of an ellipse, any line which is drawn from the center of an ellipse to any point on the surface of the ellipse reflects perfectly into the other center point. If you take the point of contact and draw a tangent line and like calculate this angle, this angle here is always equal to that angle there. So all points on the surface of an ellipse reflect perfectly from one center of the ellipse into the other. There's an interesting application of this to politics. If you can imagine, yeah, I'm going there. So some of you may have noticed that there's a country to the south of this country, right? So it's been, most of the time I like to live my life in complete ignorance of this country, but lately it's been harder and harder to ignore them. This country to the south of us has a famous building which is the center of power of the government. It's the residence of their head of state, right? It is a white house, right? They painted it white because we burned it down. And that's actually true. During the War of 1812, we burned down the president's mansion, and they painted it white, and that's why it's the White House. So within the White House, there is a room which is set aside as the office of the president. They call this room the Oval Office. Now, this may be a particular quirk of Americans, that they name rooms after the shape of the room rather than the function, but there you have it. So they have this Oval Office. Do you want to know why the Oval Office is oval? It's because of this property. It's because at any point in the room, sound reflects to every other point of the room. So no matter where you are inside of the Oval Office, you can hear perfectly anything that is said in it. So in theory, it is a room in which it is impossible to say anything in secret. This one fact clearly is the single fact that has led to American dominance over this hemisphere. It's just attributable to the geometry of this one office that they have in this one building. But it is nevertheless an interesting fact. Whoever built that office was aware of geometry. But anyway, so that's an interesting fact about ellipses. The way that SVG does it is completely wrong. It basically treats it as a rectangle with the corners chopped off. It's not even really an ellipse, Stupid SVG. The way that you should define it is by center point 1, xy, center point 2, xy, and then a radius. That's how you should define it, but SVG, anyway, it's okay. Lines. Lines are important. Lines are cool. You can draw a basic line by specifying the end point and the start point. X1, shall we say 200, Y1, 50, X2, 300, Y2, 250. Stroke! Well, actually, let's leave it for the time being. There we go. Oh, doesn't show up. Why? Stroke defaults to none. Fill defaults to black, stroke defaults to none. So, I need another CSS color.
Blue violet.
What's that? Violet?
Blue violet.
Blue violet. There you go. I have to say, I think there's a lot of violet in that blue violet.
Yeah.
I'm not sure there's much blue going on at all, actually. So there you have it. You can draw a line. Now, lines are very useful. They define the outlines of things. But a single line is a one-dimensional object being expressed in two-dimensional space. Lines do not have an area, although they can be used to define the outlines of things that do have areas. So, if we find ourselves in a position where we are drawing lines where the end point of one line is the start point of another line, which is often what you're going to be doing with lines, there's a special tag specifically for that situation, and it is called a polyline. And it has no relation to parrots. It is called poly because that is the Greek word for many, I think. Polyline. So, polylines are a little, they're a little bit differently represented than a regular line. Rather than have a very large number of attributes like this, you know, x1, x2, x3, x4, x infinity, right? You define the points on the line like so. Points. Notice I'm using my quotation marks of superstition on this one. Let's say 350, 400, 150, 300, 150, 400, 50. And again, stroke equals CSS color. Anyone? Yes?
Dodger blue.
Dodger blue. Like that?
Yeah.
There you go. We get a little hourglass. Now, you'll notice that the polyline has a fill color. If you want to turn that off and have it as a line, this is how you do it. Fill, none. There you go. Polyline. Now you may be saying to yourself, it's getting a little bit annoying having to enter the colors every single time. I wish there was some way that we could set a default. Well, I'm so happy you asked. Attributes in SVG graphics are inherited from parent objects, much like many attributes in XML. So, if we want to set a default value of fill to none, we can take fill equals none, pop that up to SVG itself. It has the same effect. So, in effect, all of our SVG objects are now inheriting a value of none for fill because they are child objects of SVG. This does not prevent them overriding the value. So, in these four objects, we are overriding none by providing our own fills where appropriate on things that have area. Here we are not, and that is we are just taking the default value and not modifying it. Have you guys done overloading in Java? Very similar concept. right? Good. So, okie dokie. Does anybody know what a polygon is? What is the definition of a polygon?
It's just a shape, yeah, a shape, but it's,
It's a shape, yes.
yeah.
We can be a little more specific. Yes? Well, triangles are polygons. I would say a shape with more sides than two, because to be a polygon, it must have area, right? And you cannot compose a figure with area of only two lines. The best you can do is you can trace over the line again, right? But that doesn't give you any area. So, number one, must have at least 3 line segments. Number two, all of those line segments must be connected, right? That is to say, it must be a closed figure. So we're not allowed to have any gaps, right? So, this is a polygon, right? That is not, right? You can very easily turn a polyline into a polygon by simply taking the word line in polyline and replacing it with gon, and we have a polygon. So, if you were writing a polyline in such a manner that your final coordinate is the same as your beginning coordinate, you can save yourself the step of writing that extra coordinate and make it a polygon instead of a polyline. Does that make sense? Any questions? Okay. Good. So, let's see here. Let's see if I'm forgetting anything. Okay. Well, I think we will we'll break for our break at this point. When we come back, we will talk about text and pathing and text pathing. Haha! Combining text and pathing. So, 15-minute break. Please be back at 11:31. Thank you very much. Can you tell I'm working really hard to try to make this lesson interesting?
See it, we noticed.
Yeah. So, text then. So creating text objects in SVG graphics is, again, quite a bit simpler than doing it in Java. We have a text element. In contrast to the self-closing tags that we've been working with so far, text is kind of a more proper, 2-tag HTML type setup. The relevant attributes for text are still stroke and fill. Stroke, CSS color. Gray. Fill?
Padded blue.
What blue?
CALLID.
CALLID, like that?
No, like this. C
Hmm?
CADE.
DE? Oh, cadet blue.
Yeah.
Yeah, there we go. Okay. Yes. Font size. $40 points. You can use, you can select font family as well. You have all of the fonts available to you in CSS. This is some text. Or perhaps, hello. Hello, world. Now, here's an interesting thing. Where's the text? Well, I see a little bit of the text. I see a little sneaky end of a comma hanging down. So, when we're dealing with rectangles, where's the registration point? Top left. Very good. When we're dealing with text, and I think this is actually one difference between SVG and JavaFX. The registration point is, we haven't specified X and Y, so they're defaulting to 0. Where's the registration point? Top left? No, it's bottom left, my friends. Bottom left registration point on text. So that's the reason. The text has been placed at 0, 0. That means that it's off screen mostly. So let's set X equal to 10, Y equal to, oh, I don't know, 60? There you have it. Now, this makes things annoying. If you're the type of person who likes things to be neat and clean, if you want the gap here to be the same as the gap there, because that looks nicer, you're going to have to manually fiddle with the numbers because, your font size is what you have to offset by the font size, but there's no perfect correspondence between font points and pixels, right? So you basically just have to manually play with this gap to get it as close to the other one as you can, or register it, or make it offset from the bottom corner, the bottom left corner instead of the top left corner. That's the other way of doing it. Make sense? But you guys should be well and truly used to how fiddly this stuff is by now. So, good. Question?
So, what happens if we change the viewing breakpoints then? Is that gonna mess up how the offsets?
Do you mean the size of the SVG object?
The content inside of it, would that throw things around?
The text? No. More text. It'll just draw it off screen, that's all. So you have to manually insert your line breaks. And the way that you do that is with T-span. T-span. What? Insert mode? Why am I in insert mode? That's stupid. There we go. Oh, come on. Did I get it wrong? What is it? T-span? Oh, man. You're not making this easy. So you're like manually in control of your line spacing. This is like really not a great text rendering engine. Yay! So there you have it. That's how you do multi-lines. Any questions about text?
So essentially, it's non-responsive. If we shrink it, like the box itself is going to give us a horizontal scroll bar.
Yes. Well, no, the SVG graphic itself will not expand to accommodate its content. Like, for example, if I knock width down, it just cuts it off, and it doesn't introduce the horizontal scroll bar. So this is like, this is one thing about SVG, which is kind of like, right? Yeah, you're kind of stuck working in pixel values. There is a way to scale it, but let me get through this. So we also have a type of object called a path, and we can write text such that it follows that path. But first we need to learn how to write a path. So neither of the other two classes I've taught have had any idea what I've meant by this. Never seen this program before, but has anybody heard of the Turtle drawing program? Hey, there we go. You guys, yeah.
For Java, right?
Well, it had a lot of implementations in a lot of languages. But yeah, so drawing a path in SVG is very similar to the Turtle program. Let me show you guys what the Turtle program is. You remember Google. So, yeah, this is an implementation of it for Python. So, the Turtle program was a program that was used in elementary schools, at least in the elementary schools I was in order to teach basic programming skills, like very basic programming skills. The idea is that you have the turtle, but the turtle is just a cursor, right? The turtle is a cursor. You give the turtle commands, like go forward by X amount. You start here, go 80, you go 80. The turtle has tank controls, so like you can go forwards and back and turn. So turn 90 degree turn. You can then put in little loops and that sort of thing. So, and this is like in Python syntax, which, the original ones didn't have Python syntax, but, go 10, turn 10. You repeat that a number of times. It draws little line segments that curve around and look like a circle. Like this is the idea behind the Turtle program, right? You have a cursor that is on the page. You can give that cursor instructions to move over here, move over there, lift the pen, put the pen back down again, right? the pathing that we're going to do in SVG graphics also includes drawing arcs and splines, which things are going to get a little mathy for a bit, but that's okay, because you have me. I will help you through the math. So path. Someone give me a CSS color.
Fire brick.
Fire brick. Very good. So the path for the path instructions are consumed by an attribute called D, and there are little instruction codes. If you take a look in the notes, you have lists of instruction codes. So, so first of all, very important, all paths start off at 0, 0. So normally, the first command in the path is to move the cursor to the starting position of your figure, right? So M is move to, x, y. This is a move to with pen lifted command. L is move to with pen down. So that is draw a line from previous position to this next position. Each time you enter a command, it uses the position of the cursor as implicitly the position you start at. So if I'm drawing a line to 5, 7, but I'm already at 3, 8, I go from 3, 8 to 5, 7. There are also commands for only moving horizontally and vertically, but those are like subcommands of line. Z draws a line from the current position to the first point of the path, that is to say, close the figure. So it is my suspicion, although I don't know this for sure, that the engine that underlies polylines and polygons is this thing, and that the difference between a polyline and a polygon is that a polyline does not have Z as its last instruction, but a polygon does, and that's the entire difference between them. So, let's write some commands. So let's move to x is 500, y is 50. Line to 550, 50. Line to 550, 100. Line to 500, 100, z. Let's see how this renders. It doesn't! Yay! Okay, let's take a look. Oh look, it's inside of my text. That will not work at all. There we go. So there you can see. Oh, I meant to do a square. Why are you not square? Let's see. 5 to 50. 550, 550, 50. Oh, missing one. 500, 100. There you go. There is a square. Ta-da! So, similarly to a polyline, this thing also has a fill, which you can use. I kind of want to erase the text because it's a bit in the way. Maybe I'll just make it small. There we go. So, there you go. That is a path which draws a square. And as you can kind of see from this, this is kind of like a little bit more like getting at the spirit of vector graphics. Because another term, another mathematical term that you use for coordinates is vectors. So you have coordinate vectors, vector graphics, right? So that's a path using straight lines. Any questions? Shall we discuss curves? So, earlier on today, I made the comment that the Nike logo is just two splines, right? Spline 1, spline 2. And I know that's like a bad version of the Nike logo, but yeah, there you go. It's two splines, right? So this is how splines work. All right? You take a line segment, between 2 points, right? You add to this 2 control points. So a control point designates a line segment that is tangent to the curve at that point. You guys know what tangent means? So,
Opposite direction.
nope, not quite. So if you have a circle and you have a point on the circle, the tangent line at that point is a line which passes through the circle, which is perpendicular to the radius. Right? So that is to say, it is a line that touches the surface of the circle but does not enter the circle. In order to do this, it has to be perpendicular to the radius, right? So that's a tangent line. So when we make a control point, say here, the curve is made such that the line from this point starts off tangent to this line, right? If I put another control point in over here, the line has to be tangent to that curve as well, and then using mathematical formulas, they kind of fill the gap, right? So this is called a spline. If you've ever seen there's a common meme in video game loading screens, reticulating splines. These are the reticules that you are reticulating splines with. If you have more than one segment, it's very common that this control point will be reflected so that it's sort of a continuous segment like this, because it should be tangent on both sides in order for you to not kink the line and have like an angle in there, right? A basic tool that you can use to play with splines is actually embedded in Microsoft Paint, as well as probably any other image editing tool that you may care for. Paint? The curved line tool, right? The curved line tool, how many people have, is it safe to assume most of the people in the room have played with MS Paint? Yeah, okay. So when you draw the curved line, you have to specify 4 points. The starting point of the line segment, the terminating point of the line segment, then the control point of the first point of the line segment, notice that no matter where I move the cursor, the line segment is tangent to a line. If you were to like draw an imaginary line between the first point and the cursor, that curve is tangent to the line at that point, right? So I can say, let's put this down here, then make a second tangent point over there, right? There's one curve. Make the tangent line a little long. Like the length of the tangent line also like controls how far the curve goes. There we go. And there you have it. Something that looks approximately like the Nike logo. 2 splines, right? Now, I very, very highly do not recommend manually modifying SVG text in order to design splines. It's very useful to be able to pull them around and see how they change, right? What you want is a vector graphics editing tool that you can do this with, because oh my goodness, all right? So if you're doing any serious work in vector graphics, get a vector graphics tool, export it to SVG, right? Take that SVG, pull it into your HTML, then you can JavaScript it up. Yes?
Yeah, so when you say a vector generator or vector image, is this something that is embedded with a lot of these tools like Photoshop, or is this something purely independent on its own?
Photoshop will do it, but SVG editor, if I just pull something up, first link, let's see here. Yeah, this would probably work. Oh, except they want money. They will often want money. Ooh, let's say open source. Inkscape. You know it's good. Okay. You know it's good when they list what operating systems it runs on, they list Linux first. That's how you know it's good software. But yeah, Krita probably does this as well. But the most important part is that it exports to SVG format, right? Yeah. I'd have to like download and
When
play
you
it.
like, is SVG format still like an image format, or is it more of the way that you can, it's like a script that you can copy into?
It's XML. SVG
Okay.
files are XML files. So right? Open image, new tab, let's see here. cat.svg, save, download, save, open. There you go. Now it's a little bit, this is a little more complicated because, it's a little bit more complicated because it's good and got some detail and
Yeah.
I personally, I look at this file and I was like, oh yeah, an image editing program made that, not a human, right? Like if you see just a wall of numbers, you know you're looking at something that's been generated, And I can tell when I'm looking at your assignments too. Some people put SVG graphics into their assignment ones, and it was like, oh yeah, that was either made by you, but probably not. You probably just got it off the internet. But like I'm kind of like, I was like, cause it turns up on like the plagiarism checker, but I'm like, well, you know, if I let people copy in like PNGs from anywhere, you know, SVG is probably fine as well, it's just an image, right? But we can, you know, just take a look at what this SVG is actually composed of, right? I don't see any rects, I don't see any circles, I don't see anything but paths and groupings of paths, right? And one particularly long path. But that's it. That's it, right? So you could literally take this code, like you might have to take the header off, right? But everything from opening SVG to closing SVG, copy that, paste it, apply some IDs, right? And you could hook up a JavaScript event to click the kitty cat's nose and make his whiskers wiggle, right?
Right.
But yeah, so yeah, that's what the file format you're working with is,
Right.
right? Yeah, good. Any other questions? Cool.
Does it have to be embedded in your HTML file, or can I just call it the way you call an image? You still have it just as a string.
I'm pretty sure you can just see. The question I have is like, if you just load it through image, like if you load it through the image tag, would assigning IDs inside of it work? I wonder if like SVG has a source attribute. Doesn't seem so. href? It has href. I'd have to play with it a bit more, but I think you should be able to like import an SVG file using href. I'm not sure if that would break JavaScript integration though. That's the only thing.
Yeah.
But it shouldn't. I don't think it should, because you're just loading XML, right? So, like, my concern is like if you loaded it through the image tag, it would kick the whole file out to the rendering engine, and then the rendering engine would just render it and then give it back to you, right? But if you loaded an SVG using href using the SVG tag, my suspicion is that it would load the XML as XML, so if you dropped image like ID tags inside of it, those would still be loaded, so it would still work with JavaScript. But I would need to test it.
Right.
Yeah. Any other questions? Good questions. All right. So, in addition to this, which is called a cubic Bezier curve, we also have quadratic Bezier curves. The main difference between a cubic and a quadratic is that in the quadratic, the two control points are actually the same point. So you draw 1, 2, with a control point 3, you have lines coming like this, which define a curve. Does that make sense? So you can't get like a swoop up, swoop down with one of these, right? But they require one fewer coordinates, so they're a little bit simpler. This is the one I'm going to demonstrate. Pardon me, I just need to tie my shoelace. So, yes. So, we have two additional instructions. Q for quadratic Bezier curve, that's that one, and C for cubic Bezier curve, that's that one. Let's add a quadratic Bezier curve. I'm going to replace this line with one, Q. I'm going, so it wants you to you have to specify the control point first and then the end point. So I'm going to make the control point up. So 525, 0, 550, 50. And then looking at our example, you can see I have deflected the line segment out towards the control point. Does that make sense? Any questions? So, now, let's do text pathing. We can get text to follow paths. In order to do this, we need to assign an ID to this path. ID is equal to Gesundheit. ID is equal to my path. Why be original? I'm going to create a new text object. So the way this works, in the same way that you have to create T-spans to do multiple lines, you must do text path to do a text path. You use href, targeting ID my path. That links this text path to the path with that ID. Then you just put in some text. Now, ta-da! Some text. You can see that basically what it's doing is it's rendering, like it's picking spots along this line, saying, okay, I'm rendering the S there, the O there, the N there, the E there, the T there. Like it's not warping the font by doing this, right? It's just placing it at different places. But still, you know, text. Any questions? Yes,
Can I see the code again?
absolutely. You can create a text path where the path itself is invisible, and then it looks like the text is just floating and wavy as well. Yes. Good. Okay. So, if I see any text pathing on assignment 4, I shall be sufficiently impressed. So, we are through all of the shapes which I care to show you. There's another shape called an arc, but it's like complicated and difficult to explain, even more so than the stuff we've seen previously, and like you have to set flags and stuff, and I just like, how about this, okay? I will make a solemn promise to you. I won't put this on the exam if you don't require me to cover it in class. Do we have a gentleman's agreement? All right, good. So, if you want to do arcs, then, you know, go for it, but basically you can get there with the curves we've already covered, basically, anyways, if you're willing to work for it. But it's like, an arc is like a segment of a circle, right? So many degrees, but anyway. So, you can use SVG graphics to do stuff, draw proper images, but I'm not really so concerned about proper images at the moment. Let's get back to the actual bloody point of this class, which is JavaScript. So, as I mentioned at the beginning of all of this, we can operate on elements of SVG graphics the same way that we operate on any other elements of HTML. SVG and HTML are both XML formats. You guys know what XML stands for? What? I almost heard it. What does the X stand for? Extensible, yes, extensible markup language. Very good. Both SVG and HTML are subsets of XML. So, let's hook up one of our things in our SVG graphics to an event. To do this, we will need a script. Foo.js, because I don't give a foo. Ha ha ha. Oh, SJ, whoops. There you go. Alright, so, first things first, because we are grabbing references to elements of the DOM, let's do window dot add event listener load. There we go. Function. Wrong one. There we go. Binga banga boom. We need to grab a reference to the element of the SVG thing that we want to grab. In our case, let's assign an ID to the circle. Call that bar. Let bar equal document dot query selector bar. There we go. And of course, just to make sure everything works, it's always useful to log this to console. There we go. There we go. So you can see that we pull out the proper reference to the circle from. Is there a joke at the back of the class that you'd like to share with the rest of the class, guys? Thank you. So we've managed to successfully extract a reference to the circle into JavaScript. We may now do JavaScript-y things with it. For example, bar.add event listener, the hello world of event listeners. Click. Function. There we go. Just like so. Now, console.log. Ouch. There we go. Clicking tends to be a little bit more precise in SVG than elsewhere, but not sufficiently so that you'd want to use SVG anytime you're not doing a dedicated graphic. But there you have it. We can launch an event using our regular mouse events based on SVG objects. Now, it may be interesting to actually modify the attributes of SVG objects from within JavaScript. But we are not in quite the same position here that we are in HTML. With regular HTML, the HTML is processed into the document object model. The document object model takes all of your HTML attributes and maps them onto fields of the object, right? We have paragraph.style.color. We have we have image.source, right? All of this stuff. Because SVG is not HTML, we don't have all of this available from dot syntax. So, we have to use the general mechanism that that JavaScript provides to access these attributes. We have two methods. Get attribute and set attribute. There we go. This .get attribute fill. And it's purple every day of the week. So, I'd just like to dwell upon this for just a moment. All of you have been using this in Java fairly extensively at this point, I would imagine. Anybody care to give me a, what does this do in Java? What are the semantics of this?
It pulls the current instance of object.
It pulls the current instance of the object. Yes, so you might also say that this is a reference to the object that the method has been called on, right? So this occurs inside of a method, right? It is self-referential, right? I believe in Java you mostly use this to break, sort of jailbreak local instances of variables out of, like to differentiate between an argument coming in and the instance variable that's attached to the class rather than making it local to the method, right? So you also use it for scoping, to pop yourself up to the next level in scoping rules in Java, right? So in JavaScript, it's a little bit different. JavaScript generally doesn't have classes. We have objects, but we don't have classes somehow. When you use this, in this context, it is a reference to the object the event listener has been applied to. Right? This is a related concept to how this works in Java, but your usage in Java so far will be fairly different from its usage here, right? In Java, there's really no need to say, you know, this dot run method. You can just say run method because you're already, like, you already know what context a method would be run in if you're inside of a class, right? It's the class. Here, there are no classes, so there are no contexts like that. But this is still used to refer to the object to which the event listener has been attached. Does that make sense? Hopefully hopefully this is intuitive. Ha 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 ha. I really hate talking about this because it's like if you had like an operation called like but, you know, it's like it just messes up your whole speech, you know. But anyway, so this .get attribute fill. We specify what attribute we want to read by providing a string representing that attribute's name. Let's make a short little program that toggles the color of the circle when we click it. So if this .get attribute fill is purple, else otherwise, if this .get attribute fill is purple, this .set attribute fill is, someone give me a CSS color.
Spring green.
Spring green. Nice. And since nobody said it, it's been the elephant in the room this whole time. Peach Puff. Ooh, except I need to now fix this as well. Fix my logic. Get out of here, you. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There you go. So, set attribute works very similarly to get attribute, except it takes one parameter, and that is the value that you are setting. to contrast this to Java, because Java you've been using getters and setters quite a bit as well. In Java you would say something like get x with no arguments, right? Here you're embedding the name of the variable that you're getting into the identifier, right? In JavaScript, get attribute, you take this, you make this the first argument, and that's how it works. Right? Make sense? Good. No questions? So, we can do some slightly more interesting things here as well. Yeah. Well, I have like a longish example that I want to do, but we're kind of running out of time. So I think I might save that for next week and press forward with object creation and destruction in HTML. So, okay. So we're going to depart from SVG for a moment, and we're going to return to it next week. But right now, I would like to show you how it is that you can create and destroy objects inside of either the document object model or inside of SVG graphics. So, let's recall the structure of the document object model. It is a tree. HTML, body, head. Body might contain an H2 and a div, something like that. So, let us remind ourselves the naming convention for relationships in this graph. Body is the child of HTML. HTML is the parent of body. Body has two children, H2 and div. Both H2 and div have a common parent in body. They are therefore siblings. Right? So, let's make a new HTML page. We'll call this create.html. So, let's make a div. Yeah. There we go. Don't even need an ID. So, I know I'm not supposed to do this. There we go. So, when we load this div, or okay, so the object of this demonstration is to, let's make a button. Every time the button is clicked, we add a new paragraph to the div containing some text. So we'll also need a button. On click, spawn, and button. button text, create child. There we go. Now, let's create that function. Function spawn. There we go. So we need a reference to the div. Document dot query selector div. There we go. We're going to do something with that. So this is how it works. When we attach a new element to the DOM, we can't just magic it up out of thin air. We have to create that object first in JavaScript and then issue a command to attach it to the div. So, we can create DOM elements document dot create what is it? Oh, I'm forgetting. Come on. What is it? Create. It is create element. Create element. You then specify what kind of element you're creating. For any of you who want to immediately apply this to the SVG graphics you've been working on, this method requires slight modification to work with SVG. For now, let's stick to vanilla HTML constructs. Okay? So, let's create a new paragraph. New dot inner HTML will be equal to it's my turn. Yeah. Can you tell I have children? So, or maybe something else, maybe just like spam, spam, spam. There we go. Spam, spam, eggs, and spam. There we go. That's better. So, we've created a new element. We've given it some contents. All that remains is to hook that up to the div. We have a lovely function for this called addChild. Is it addChild or addChild node? Let me see here. It's appendChild. There we go. AppendChild. Yeah. Man, when I get hungry, the first thing that goes is my ability to remember method names. You then pass the reference. Oh, yeah, it's not going to let me use new because it's a keyword. Oh, P, new P, new P. There we go. There we go. So we pass the reference to the newly created object, like so. Save that. Let's open up that file. There you go. We can add as many versions of spam, spam, eggs, and spam as we want to our div. Cool? Does this make sense? You guys want to see the code? Does this make sense? Any questions? Would you like to see the method for removing things now? we create things and now let's
Destroy them.
Alright, so there are a couple of ways that you can destroy all children. One of them is to very simply overwrite the inner HTML of the element. So if I just set interval, give it a function, say every 3 seconds we execute document.querySelector div.inner HTML is equal to empty. There you go. Every 3 seconds, it eliminates all of the contents. Now, that's okay. That's like the nuclear option, right? That's not going to work if there's other contents of the thing that you want. Also, kind of the whole point of learning how to use create and destroy methods is to learn to avoid modifying inner HTML in order to perform object creation and destruction, right? We are looking for more sophisticated weapons of more civilized ages, right? So, we also have remove child. Let's assign the div to a variable for now. So div.remove child requires a reference to the child we are removing. We can access the list of children that we have attached to the object. Div.children, it's an array. Perhaps we erase child 0. If we add a little variable here to be able to distinguish them, let's I equals 0, put I in there, there we go. Every time we spawn one, I++. So now it tells us how many times, right? You'll notice that these are now being deleted from the top to the bottom. We are deleting the oldest ones first, because we are removing child 0 once every 3 seconds. Make sense? So this is okay. Another thing that you can do, and we're kind of like, at this point we are leaving far behind us the safe shores of things you could do in HTML, alright? Check this one out. New paragraph dot add event listener. Click. Function. This dot remove. I think this dot remove works. Yeah. And now you can remove them by clicking on them. So, if you're one of these people who has been thinking to yourself, add event listener, that's long and complicated. I can do that through HTML with onClick. Well, you can't do it with onClick if it didn't exist in the HTML page to begin with. right? So, there is a reason that we've been showing you this, right? Make sense? Did I show you guys the demon summoning comic meme thing? No? You want to see it? Okay, it's funny. It's also related. All right, here we go. So, programming versus demon summoning. Must know language unspoken by mankind, programming, and demon summoning. Requires that you be exact or suffer dire consequences, programming, and demon summoning. Involves much cursing, swearing of oaths, and pleading with higher powers, programming, and demon summoning. Not understanding the true power you wield or the consequences of your actions, programming, and demon summoning. Sometimes you have to execute a child, programming, and demon summoning. Candles, just demon summoning. So, yes. I don't know if I have time to get into another topic. All right. I will now open to motions from the floor. Do I hear any motions to dismiss? Does anybody wish to forward a motion to dismiss class?
Yes.
Okay, you have to put your hand up though. You have to put your hand up. You forward the motion. Do I have a seconder?
Actually, I'm just trying to.
Oh, you have a question?
No,
Yeah.
I'm just trying to get the lightsaber with you through the force.
Oh. Well, I think you need more training. So I need somebody to second though. Anybody second?
I second.
Okay, all right. That'll put it to a vote. All in favor of dismissing class say aye.
Aye.
All opposed say nay. The ayes have it. See you next week.